And we are live. Well, welcome to the Engineering Internal series at SingleStore. So this is the second episode of this Dream series that's going on. I am super excited today. So we're going to talk quite a bit about storage layers. So before I do that, I want to introduce myself. As you remember me, I'm Shireesh Thota. I'm Senior Vice President Engineering at SingleStore. I have the pleasure of talking to Joseph Victor today. He's a principal software engineering / architect at SingleStore. Let's hear about his background in his own words. Joyo?
Yeah, I've been at SingleStore for 8 years now. I came here directly after finishing my math degree at Stanford and dropping out of my PhD. And I've worked on everything from our pipelines ingest to more recently separation of storage and compute and global storage. And I'm excited to share it with you all today.
That's awesome. Joyo is a long timer here, and he definitely has the similarities with some of the elites who dropped out of the college. So today, we're going to talk about storage layer. Storage layer is, of course, the fundamental building block for any database system. And it ties into the aspects of durability, I/O performance for various operations, and the layout semantics to do indexing and whatnot. Now, and then separation of storage and compute is also, completely independently, but very related, is one of the biggest things that came out of the evolution of cloud. It came out in conjunction effectively with the evolution of cloud. Most of the vanilla database systems use it extensively. So in today's episode, we'll look at how SingleStore does this and yet preserves the transactional and analytical capabilities. So let's dive in. So Joyo, to begin with, please explain the data structures involved here. Let's start with the skip list, row store in memory, the column store in disk, etc. The things that SingleStore is very famous for. Please start there.
Yeah, so SingleStore's data layout for querying is fairly simple. It is a log sequence merge tree, an LSM tree, just like most modern databases. The bottom layers of the LSM tree are nice column store files, but they're column store files that are they're optimized for seeks. So they're built in kind of a very clever way so that you can do seeks, you can do updates, you can do these sorts of things without sacrificing any of the scan speed that you would normally get from column store, including vectorization and SIMD and all that. And the top layer of this LSM tree is an in-memory skip list. So as many of you probably know, we used to be called MemSQL, as in the in-memory database. We, of course, we're a cloud native solution now. We write to S3. That's a terrible name for us. But our legacy of having this awesome in-memory lock-free skip list to use as the top layer of the LSM tree kind of allows us to have sort of a hybrid approach to our data layout. So actually, it's kind of funny. When we were first building this thing, we called the project SingleStore because it was row store, it was column store, it was one data structure, one complex data structure that can do all kinds of different things. And I guess we liked it so much that we named the company that.
That's interesting. So I basically hear a couple of things here. Of course, the skip list in memory, and that is there, and that is sort of the legacy of the in-memory OLTP roots that we have with this company. And then the column store, I heard you say seekable, of course it's immutable. Those are some really interesting characteristics, and I'm pretty sure the audience would love to learn a little bit more into it. But before we go into that aspects, I do think that we should start with durability. Obviously, storage is required for that. That's an essential characteristic. SingleStore was MemSQL in previous life, and it was effectively an in-memory OLTP system. It evolved quite a bit to bring the Translitical HTAP real-time analytics scenarios. So Joyo, please unpack, how do we achieve durability guarantees through these various scenarios? And along the way, perhaps, please walk our audience through the life cycle of a unit of data effectively, right?
Yeah. So so let's just dive right into it. So the high level structure of SingleStore is we're of course a distributed database, and we're split into shared nothing partitions. So each table has an optional shard key, which says where an individual row is supposed to live, And the partitions are managed mostly independently with some important caveats that I'll talk about at the end. So you zoom in on a partition, and that's where the durability happens. So the durability is managed locally on each partition, and you have an LSM tree where the top layer is this in-memory thing. But the in-memory data structure, obviously, that's not durable. We log every write to this in-memory data structure. So if you want to write to the skip list, you say I've inserted the skip list. You update something in the skip list. You put another log record that says you update it. You updated that row, and this data is it is synchronously written in memory on some number of nodes, however you configure your durability, and asynchronously written to disk. So our commits actually don't touch disk, and they don't touch the remote blob store. So the commits are very fast and very stable. You can always predict the latency. So I like to call this integrated durability and compute. We would never give it this name if the words separation in storage and compute was not such a huge buzzword. But the real difference between SingleStore and our competitors is this integrated durability and compute, while still having separate storage for historical data. So I have a little slideshow that kind of just goes through an example, and I think that this example has enough detail that you can kind of figure out how most of the things work. So on the left, I have the skip list, and I also have the data file metadata. I mentioned there's these column store data files. We'll see what that metadata is in a second. And on the right, I have the log, which is written asynchronously to disk, and the physical data files, which also reside either on disk or in blob storage, Amazon S3, Azure Blob Storage, Google Blob Storage, etc. So as I said, you want to write one row, you write A1, and it puts it in the skip list, and there is an insert log record in the log. Makes sense. I want to write some more stuff. I put another log record in the log saying I've written some more stuff. And one interesting side note about this is that there's no data dependency between these two pages. And so what could happen if both of those two transactions happen at the same time? They can actually replicate out of order. Replication is considered committed when the page of the log is received in memory on some number of replicas. They don't even have to deserialize it. They just check the checksum. And this means that you can kind of send log pages out of order. So fast transactions never have to wait for slow transactions. And still, once a transaction is acknowledged, it is guaranteed to be durable unless there's a total disaster and you lose all your nodes. So our replication is very fast and very, very predictable latency. So, of course, you can't store all of your data in the skip list. You have to eventually write it to disk, and when it's big enough, it's actually better if it's not in column store. It's better if it's better if it is in column store, so you can do fast analytical scans. So the eventually a flush to disk operation happens. So you can see over here, it creates this file. The file is named file 3 because it was created on page 3 of the log. And of course, in the same transaction, we delete from the skip list. I'm kind of being a little fast and loose about my transactions in the log, but whatever. And you can also see that in this data file, it is stored in a column store format. So you can do fast aggregates, fast scans. And we also get this metadata. We say, I remember that I have this, this data file at LSM3. It was created at LSM3. Here's the types of it. Here's the maxes and mins. Here's my Bloom filters, whatever it is I have. And I also want to remember that none of the rows are deleted. Why would the rows be deleted? I just created it. Well, let's say I want to actually delete one of the rows. So if I want to delete one of the rows, these column store data files, it's really not easy to go in and change the data file. So the data files are immutable. What is not immutable is the metadata. So when you actually delete one row from a data file, you'll get something in the log, the same log that tracks the skip list updates, that says, hey, find the metadata for the file at LSM3 and update the deleted bit vector to be this. Now the deleted bit vector says this. And when queries come in and they actually do their scans, they're going to read A, skip B, read C, read D, And of course, this is all, when possible, this is all SIMD, and this is all just insanely fast. Not just SIMD, but like operations on encoded data, bulk operations, all these things. Similarly, so we can do deletes. An update is basically a delete followed by an insert. So here, in order to do this update, we update the metadata to say that C is deleted, and we insert this row back into the skip list. And this gives us, of course, the nice property that hot rows, recently updated rows, because if you update a row, you might update it again, tend to be at the top layer of the LSM tree. There's a few more tricks that we do about locking, so that you can do high concurrency locking. This is a big topic, but
maybe Joe, I would probably take a minute here to summarize this thing. This is a lot going on here, and of course quite amazing stuff here. So if I were to summarize this, the data comes into the skip list. You synchronously commit to replicas in memory and asynchronously move it to the log for durability. Of course, it's durable because of the high, and there's a high availability built in because you can have configurable number of replicas. So the data is really fast. The writing is really fast. It's appends into the memory and then you asynchronously put it to the log. And then further asynchronously, you move the data to the disk through the metadata in the data files. You pack the data into the data files, and these data files are immutable. The metadata is basically tracking how far what the progress is, and it has a bitmap which talks about the sort of the latest state of the data files. And these metadatas are always pinned in the memory, or can they?
That's right. The metadata is always pinned in memory.
Yeah, and skip list too, right?
Mm-hmm. Yeah. The metadata is actually stored in the same lock-free skip list. That is not an important detail. Right. That's just like the easiest place for us to store.
No, it makes sense. It totally makes sense. And then the usual updatability of column store is, of course, to have some invalidation, and then we are using the metadata to do the invalidation with a bitmap. It's a deleted bitmap, and then you go do that. That's sort of like a usual trick, and it's very elegant here that we're using that together with the skip list. And then, of course, you're packing the files to the adjoining to the log. You mentioned something really interesting that I think a lot of people would find it kind of it might be intriguing, that the transactions can be replicated out of order, right? And that's great because obviously it could go in different orders. So that's actually quite nice to hear that. Yeah, please take it forward, Joyo. You want to? Please go ahead.
Yeah. So regarding the out of order transactions, what's really going on there is like, okay, you got two transactions coming into the server, and the server, serves those transactions and replicates them in whatever order. But it doesn't send an acknowledgement back to the user until they're replicated.
Yeah.
And so if there's a failover, there might be holes in the log because of the out of orderness. And that's fine, because anything that's missing on the new primary after a failover was never acknowledged to the user.
Yeah. So from a user's point of view, order is maintained.
Exactly.
Yeah.
Right. So you might go forward in time, but never back.
Got it. That makes sense. Yes. Please move. Do you want? I mean, I'm very interested to learn. I'm pretty sure everybody wants to learn a little bit about the separation of storage and compute. But do you want to walk through some more lifecycle examples here, or should we go into the?
This is all I got. The other high level picture I want to point out is simply that we have this nice linear log after the fact, and these linear log have these special pages that says I'm creating a data file here. And so that is going, and these data files are immutable until they get deleted, which is going to be another record that I didn't show. And so that is going to be incredible for when we actually do separation of storage and compute.
Yeah, I can totally see already how this architecture is nicely setting it up, teeing it up to do the separation of storage and compute. And of course, it's a key technique for building cloud-native databases. And the funny thing is that it's obviously born in the analytics side of the spectrum, but even the transactional databases have started doing it. If you kind of look at Auroras of the world, they have also started doing it with a slightly different constraints, etc. So I'm curious here. Now, it has clear benefits, but it also brings challenges to achieve certain characteristics, especially the low latency guarantees. So Joyo, please help us understand how SingleStore's architecture helps navigate those constraints, and in general, talk about how you thought about the separation of storage and compute in the context of SingleStore.
Yes, absolutely. Okay, so let's talk about separations of storage and compute. So the basic idea here is we have this linear log, and every once in a while, every minute or so, because we don't expect there to be huge disasters. Although it could be faster also. We will upload a chunk of the log. But before we do that, we will actually, for every create data file page in the log, we'll go ahead and just upload that blob to S3. So S3, I use S3 as a placeholder for any object store. I'm sorry for saying the brand name; it's just force of habit. But we upload it to the object store, and basically the blobs get uploaded to the object store as soon as they're committed, but asynchronously the chunks of the log also get uploaded to the object store. And then this is really nice because now you have basically every piece of data that you need to rebuild the database in something with 11 nines of durability. And it's also nice because you can do the bottomless storage thing. You can do the unlimited storage thing, where as soon as a piece of data is persisted to the object store, you can just delete it from local disk. So local disk is kind of like a cache. It's kind of like a write-ahead cache, where the local disk is used for durability up to the point where the thing is persisted to S3, and then now it's just a cache. So you only have to have enough disk to store your working set that you need to query, and that is really nice. And that's a thing that the analytics databases, they've had for a long time. That's Snowflake's whole thing, BigQuery, Redshift now. But if you write one row to Snowflake, if you write one row to the data warehouses, it's going to S3, and your latency is going to be whatever it is. You write one row to SingleStore, you're not hitting local disk, you're not hitting blob store. It'll happen in the background, and the replication is responsible for durability. So that is how our separation of storage and compute is quite different. There's of course a lot of familiar benefits to this. I mean, the benefits are just so many, and they're so
before we go into the next steps of the benefits, and I totally see them, just to kind of capture these things here. So the uniqueness of this is that obviously a durability is guaranteed by, first and foremost, the high availability of replicas, then the log, then the disk, then the object store. What you said is very interesting, that the disk kind of acts like a write-ahead cache, because it's sort of, if you don't have an object store, then that's the bottom layer, that's the bottommost layer, and that has to be the durability guarantee layer. But if there is an object store, you sort of keep moving the data, and you can keep making space into the disk, and then that becomes like a write-ahead cache. So only to the point until the data is not moved out of the disk to the object store, it's where the durability comes in. So that's beautiful. And is the data that's moving from the disk to the object store, is it exactly the same? Do we do anything different in terms of changing any formats, or is just take the files, byte by byte?
We compress it.
Yeah.
Yeah, so it's stored on disk in column store compression. We'll put an LZ4 on that. Sometimes we get another 50%, but that's it.
Yeah, but just same thing, compress it, move it to the object store. So that's really, really cool. Yeah, and you talked about checkpointing here. Can you talk a little bit about that as well? Yeah, how does the checkpointing work? Yeah.
Right. So most B-tree based databases are going to have some notion of checkpoint, where they have to kind of move the B-tree pages around. For us, our checkpoints, we actually call them snapshots internally, but the checkpoint is more similar to the industry standard term. And what these things do is periodically we'll upload a file that kind of looks like a log file, but only has inserts in it. And so it has the state of all of the in-memory skip lists and all of the column store metadata, and obviously your tables and your stored procedures and your pipelines and the pipeline metadata and all these things. And it does this at a specific version, which we haven't talked about yet. But it gets a globally consistent snapshot, and it uploads it. And it's just a file such that if you replay that file and then you replay all of the logs after it, you get the same thing as if you were to replay all the logs since the beginning of time.
That's very nice. So yeah, I mean, I think there are a few things that are coming clear now, right? Which is you don't have to touch the object storage in the right path, unlike the traditional data warehouse systems. You basically have the usual classic sort of almost like an operational kind of system on the top, and then you sort of evolve into the separation, proper separation, and go into the scan perf. But you also get the other benefits, right? Because of this, you now can do like independent provisioning and sort of like really cheaper storage for pause and resume, etc. So let's talk a little bit about that, right? And we talked a lot about the provisioning of replicas for various reasons, right? You do it sometimes for storage reasons, and in this case it's less so because you actually have an object store underneath. You do it for HA because you just want more redundancy and whatnot. Then you typically do it for throughput as well, right? You just want to have more traffic being served. And when that happens, I think the biggest problem that I've seen in most of the systems is that replica needs to be always alive, because it's constantly taking the traffic. So if it's not alive, then it needs to do a huge catch up from the primary, which could take a lot of traffic away from primary. But here, there is 99% of the data is in the object store, right? So please talk us through a little bit about that, which is effectively, really, the way I think about it is that it is sowing the seeds of elasticity and enabling auto scaling and all that kind of stuff. So please explain on how you build on the object storage, the separation of storage and compute capabilities. You call it bottomless. How you build on top of that and enable these nice characteristics.
Right. Yeah. So as I mentioned, the checkpoint files, they store the skip lists, which are smallish. They store the metadata, which are small relative to the data. They don't store the actual column store files, which is great. And they store your tables and stuff. So if you were to if you were to want to provision a new replica, what do you actually need to come online? Well, you need all this, basically the contents of the snapshot and anything that's in a log after it. So you download the snapshot, you download any logs after it, and you're ready to go. You're ready to start. If you, for instance, want to participate in redundancy, you're ready to start serving ACKs right away. If you want to do read queries, you're going to have to, heat your cache. Like, there's no getting around that. But you only have to download enough data from the object store to actually, be able to start serving queries. So if you, for instance, spin up a read-only workspace, we have this notion of workspaces where you can basically have a shadow cluster that's isolated and it's read-only and it's receiving the live writes via replication. And it just, I can spin these things up pretty fast because they don't actually have any, to spin them up, I don't need to download very much data. And I just query them. They just have to download whatever data they need to query. And of course, they'll cache that data for future use. So yeah, that's kind of an O of in-memory rows plus in-memory data file operation, which is way, way, way smaller than the many terabytes of blob files you might have.
And once you do this, once you provision this new replica, of course, you can quickly build it up and catch up to it. And then the replication quickly signs off, right? Like a lights up, right? So that, that it is consistent and it's not like you're always doing an eventual reads, that kind of stuff, right?
That's right. The latest data will of course be sent eagerly. So the queries that touch the latest data the cache will be hot for those.
Yeah, this is again a difference in terms of how some of the other hyperscale systems work, right? If you think about Aurora and even AlloyDB, I believe, SQL Hyperscale, etc. There's the replicas are typically read replicas are typically lagging, but here you immediately provision it and you get going with the new data. So that's pretty awesome. Yeah.
And of course, we have heuristics to preheat these things and like actually make a usable system. I'm really talking about the underlying storage technology here.
Right. So when you say heuristics, I mean you're trying to understand what blobs are active in the primary, and you just basically tell the new replica that, hey, these are the ones that you should basically prefetch.
That's right.
Something like that, right? Yeah, that totally sounds great. Yeah, I mean, this is kind of really, when you think about all the characteristics that we brought together here, it's 100% a fantastic translytical system, right? Naturally, you have the column store for the scans, you have the row store in the memory, as well as I know we haven't touched upon some of the characteristics about indexing that the system built on top of the column store. The recent Sigmod paper does a great job about how the indexing is done um, on the column store here, which is all really novel. And this kind of, and then you added a separation of storage and compute. That kind of really is great to do the translytical stuff. Yeah, please talk a little bit about how it is not your average column store.
Yeah, so I mean, the stuff I'm going to talk about is, a decade of work of a team that a big team that I'm not on, but I do want to touch on this stuff because, a great storage layer doesn't matter if you can't query the thing. And so I wanted to talk about why our query layer and the actual layout of the data is ideal for, both transactions and analytics. So as I mentioned, SingleStore was this data layout project originally, and so what we have is, we have every table has kind of a primary sort key, optionally. You can just have it unsorted if you want, and a shard key that lets you do push on joins, lets you do group bys, lets you really tune your queries to the max. And these things are fairly normal. But the special thing that SingleStore kind of has is we have these secondary hash indexes. And there are these 2-layer indexes that we go into a lot of detail in the Sigmod paper that basically let you do really fast point lookups on your column store data, which is crazy. So we have these secondary hash indexes, and we even have secondary unique hash indexes. So you can have, you can do upserts on your column store if you want, depending on how you do it. It might not be. It will never be as good as an in-memory skip list. I mean, an in-memory skip list is like the best data structure for something like this. But you can actually run TPCC on the column store data, and and it works. And it works. You can also do high concurrency updates and deletes. So, naively, you could imagine, oh, I want to update one row in this million row column. I have to lock the whole thing. Your concurrency is going to suck. But that's not what we do. We actually have a system for taking row locks that is it's described in the Sigmod paper. And basically what we do is we kind of have these shadow transactions that can actually move things from column store back to row store without committing anything in order to take a lock on it. And this all happens behind the scenes. The user doesn't have to worry about it. They just, run their workload and they say, oh my God, I'm running an operational workload on column store and it doesn't suck. We have seekable encodings. So all of our column store encodings kind of have the extra constraint that they must be seekable. Surprisingly, adding this constraint doesn't really affect scan performance at all. So that's a W. And yeah, so if you combine this with the fact that the hottest roads tend to stay in the skip list, the single source column store can it can get, it's not going to get as fast as row store, but it can get within an order of magnitude, which, it's a scale out system. So suddenly you have a system where you can run both transactions and analytics on the same hardware, on the same data, and it works. And of course, if you only want to do one or the other, then you can actually say, oh, just give me a skip list and I'll eat the cost of the memory. And then now you're going really fast for transactional workloads.
I think you really nicely, succinctly put together one of the reasons why we believe we are the best translytical systems, and this is the reason, right? I mean, it is honestly a breakthrough aspect here, right? When you think about all these key capabilities, who would have thought how to do seekable encodings? I mean, secondary hash indexing and unique indexing on column stores, right? I know the Sigmod paper does a great job. The fact that we could do those indexes also as log structure merge trees, I mean, the meta aspect is just beautiful. It's really an elegant architecture there. And obviously, I just wanted to bring it back to what it means to the applications, right? When you kind of think about these capabilities, you really can, we talk a lot about the real-time analytics scenarios, HTAP, Translitical, different names for it. But the real-time analytics is a killer app. We have many customers who basically want to go do, bring data in, and they want to keep on doing updates and do some CRUD operations, just like how they want to do it in the operational database. And yet they want to get the insights really as fast as the data keeps moving. So the data is streaming in, it's keeping in, and you want to run your dashboards, your insights as fast as you want to do. There's no ETL needed because the system is designed to be able to take those CRUDs, those updates, even point lookups, etc., while doing these fast scans. I mean, that's kind of really, I know there's a lot of skepticism, but you got to look at this architecture. You got to look at our paper, and we will post these links in the chat. You really have to look at it, and thank you, Joyo, for sort of like bringing them all together here in a really good way here. Again, that's kind of really, going into my next question for you, which is the whole translytical systems. We talk about it all the time. And this architecture 100% has the underpinnings to do TPCC at the same time as TPCH, DS, and obviously, if you search for SingleStore, there's a lot of good benchmarks that prove that we could do all three. I don't believe there's any database that can do all three, and we do it like really well, extremely well. The data is all in memory. If it is all in memory, we get a ton of great OLTP performance, as Joyo said. But we also go toe-to-toe on the analytical scan performance, etc. That's sort of really, when you think about all these pieces, it is just amazing. One thing that still stands out for me here, Joyo, is ACID guarantees. When you think about these capabilities, obviously there are constraints, and there are really incredibly hard constraints. You touched upon a few things, like when you think about unique constraints on a column store, etc. It's really awesome. But ACID is obviously super important to do it at scale, and SingleStore is a distributed system. Could you touch upon that? Could you touch upon that and talk a little bit about how do we achieve this? I know it's a broad topic, but would love to hear some thoughts on that.
Yeah, so ACID is, I'm not going to lie, it's actually very difficult to make it super fast and super super reliable. So for I'll go through this slide and then we'll talk about it. So as I mentioned, the cluster has a bunch of shared nothing partitions, and shared nothing, like if they're really actually shared nothing partitions, you're going to have a hard time getting ACID, period. But the nice thing is, all the logs, all the LSNs, all the uploads, everything happens independently per partition, and there's no need for coordination. One caveat I'm going to mention just up front: if you have a unique key, it has to match the shard key. So unique key constraints are always resolved within a partition. So that's how we got around that very, very, very hard problem. Anyway, so going back to the other ACID guarantees. So let's talk about isolation a little bit. So as I mentioned, all of the logs, the LSNs, LSN 1000 here, and it could be LSN 5000 on a different partition, whatever. But every transaction in the system is given an increasing logical timestamp. So there's a paper called Clock SI that we're heavily inspired by. And if you're into this kind of stuff and you haven't read it, go read it. It's very cool. But yeah, so each transaction has a different logical timestamp. So for instance, if I do an insert that inserts 2 rows, one of them's on this partition, one of them's on that partition, those 2 rows will have the same logical timestamp. And so what this means is that if I have a map from timestamps to approximate LSNs, they don't have to be super exact, but approximate LSNs, I can find an LSN in each partition, and I could, for instance, use that set of LSNs to restore the cluster to a consistent state. So we offer a point-in-time restore mechanism based on these logical timestamps that each transaction has by doing that. You could also use these logical timestamps to do snapshot isolation. Or actually, we have designs for serializable now. That's a bit more work. And we use a 2PC protocol that so it's a traditional 2PC protocol. It says that everything's atomic. So if I have a transaction that writes a row on partition 0 and a row on partition 3, they either both commit or they both don't commit. And if there's any failovers, they will talk to each other. Our 2PC protocol is a little bit unique in that it's presumed commit, which I'm sure we're not the first people to do this, but I've never heard of anyone else doing this. It's a very simple idea, but it makes the thing much faster, which is that if a partition sees the next transaction and it didn't hear any problems, it assumes commit. And this means you don't need any extra round trips. You just you just send the data. So turning on 2PC doesn't actually slow anything down, which is great. And the resolution protocol is also all peer-to-peer. It doesn't rely on a central coordinator. But other than that, it's a pretty traditional two-phase commit protocol. So yeah, that's how we maintain ACID at scale without having to have a ton of coordination or anything that slows it down. And then everything else is just partition local.
No, this is great, and of course, I completely agree with you. ACID at scale is not trivial. There are a few nuances that I want to touch upon. Of course, I think some of those who are familiar with SingleStore know that we don't have this stronger isolations levels yet. We're working on it. The architecture that Joe pointed out is going to enable us to do that, and we have the design and the underpinnings to go do that. We are, of course, on our way to do that. The thing that really I want to kind of bring it home here is that the definition of distributed SQL in the market is effectively, in some sense, simply put, is ACID at scale, right? There are lots of other important characteristics. It has to have a relational foundation, it needs to be elastic, but it needs to have ACID at scale. That's a key thing. And there are a few other things. One thing that we believe at SingleStore is that we should minimize the data movement. You should really be able to operationalize and gather insights on the same piece of data at the same time that it comes into the system. It's important because the industry as a whole is basically going into hyper specializations, and that essentially means moving the data. The modern data stacks, as it is presented, it just requires, I think, if I counted last time, it requires 5 ETLs to go do the entire thing. Some of them are inevitable. We're not trying to solve everything, but it's important to tackle this portion, which is to do both transactions analytics. And in many ways, the distributed SQL movement is sort of not really catering to that. We want to 100% focus on that. When we think about distributed SQL, we are totally thinking about doing the transactions analytics at scale, preserving asset to a greater degree, of course, having the relational foundations, and so on and so forth. Definitely separation of storage and compute plays a very critical role. So I hope that this episode really brought together that view as to how we are thinking about our journey, and it also talked a little bit about our past. So yeah, it's been really fun talking to you, Joyo. If there's anything else as a last sort of summary, please go for it.
Yeah, thank you for listening. I'm proud of everything that we've built. And, we got a lot more to build, but it's really cool to see what our customers are doing with SingleStore. So
100%, yeah, totally. The one last thing that I just wanted to just bring it up here is that we are running a hackathon, a public anybody can participate in it, and you have a chance to win $30,000 worth of cash prizes. All you need to do is to pick up a great application idea using SingleStore, of course, and there are links that we are posting it on the site. Please go ahead and look at it. It's super fun. We are really excited about the ideas that we are seeing already. I encourage everyone who's watching this to do it and share it with your friends who are enthusiastic about building distributed real-time applications. And along the way, you'll learn about one of the best databases out there, which is SingleStore. So thank you once again. Thank you for your time. We really had fun talking to Joey about this topic. See you again soon.